Okay. So I'm going to talk about JuliaSim batteries. So what JuliaSim battery is a product from Julia Computing, Julia Hub, sorry, for stimulating advanced battery models. So we have partial differential algebraic equations for electrochemical models for battery cells. These models are discretized with finite volume methods, and we have several models with different degrees of precision, starting from the most precise one to less precise models with certain assumptions. This, if look at here, I don't know if my mouse can be seen, it's like the equations that we're solving. So these partial differential algebraic equations are discretized into. Is my? I don't think you can see the bottom of the. Oh. No. No, it doesn't work. I can try refreshing them. Nope. For some reason, F11 doesn't. Okay. Is this better? Yeah, I think you can see the bottom of the. Yeah. Okay. Okay. So we have the discretization. So we have like 300 DAEs per each cell, and we can compose these cells into packs. So you can have large battery packs, and one of the advantages of competing tools is that we are much faster than similar tools in Python, for example. We also have thermal and degradation submodels, and also we support different sets of battery chemistries. And it's also easy to add your own chemistry if you need.
What chemistries do you support?
So the ones listed here, NMC, LFP, and LCO. I'm going to show a demo bit in a bit. Okay, and next. So some of the challenges in modeling lithium-ion batteries are the fact that there is a large cell-to-cell variation. So in a battery pack, you have a lot of cells, and there is a large variation in the behavior of each cell. And there are a lot of approaches where you have a one-size-fits-all approach, but this doesn't work very well because of this large cell-to-cell variation. In this plot, we have the degradation with the cycle number, and we see that the degradation for individual cells in a battery pack depends on which cell it is. So there are some cells that degrade less than others, and there are several reasons for this, which I'll go in a bit. If we go to accurate electrochemical models, they are traditionally slow to simulate, and also it's also very hard to scale them in packs. So if you have one or two cells, it's going to be very different than if you're trying to do 1,000 of them. And if you have a slow model that's already slow at one cell, if you go it at 1,000, it becomes prohibitive.
Is this also the data you're going to use to train the
Sorry?
models? Are you going to train on this data, on the discharge?
Yeah, you can also calibrate. So if you have your own experimental data, it's possible to calibrate and integrate with the SciML ecosystem to calibrate the model for a particular application where you might have your own experimental data, and in that case you can calibrate to your specific needs. So the battery modeling landscape here in an accuracy versus scale. We have tools that have very high accuracy but low scalability because of, as I was mentioning, if you have traditionally, like in Python packages that aren't necessarily the fastest ones, or you have tools that scale and are built for packs, but they usually make assumptions about, I mean, they use simplified models to do the scaling, essentially. So they are using usually equivalent circuit model. So they're based on equivalent circuits. And what we're trying to do with JuliaSim batteries is to bring these two together so you can have an accurate tool that can also scale at large battery packs. Okay. So as one of the main application for these kinds of tools, electric vehicles need very precise modeling for the batteries that they run on. So you need to be able to predict the demands on the battery in a very short time, and also with a very small error. It's also especially important to be able to monitor critical safety metrics, of course, such as the temperature. You don't want your battery to overheat. If you're fast charging an electric vehicle, you want to be able to monitor the temperature and be very sure that it's not going to overheat, and you want to look at how the fast charging will affect the degradation of the battery, what happens during use. And now, speaking of this, in the process of designing batteries, it's useful to study different chemical compositions that you might use for the battery, and in this case I'm presenting a comparison between several chemistries. So in the first plot we have 1C charge, so we have this constant current, constant voltage protocol, and we have the same protocol but we have different chemistries, and we're looking at the state of health of the battery. So it starts from 100%, and when it reaches 80%, we consider that as the end of life for the battery. And we want to compare several chemistries in order to evaluate what would work best for a given application. And this is something that can be used to inform design decisions around what can be used, what are the costs associated with several chemistries, what would be the expected outcome of using a certain chemistry in a battery, and also how does this change with the charging and discharging behavior. And one obvious thing that we can see here is that if you charge the battery faster, it's going to also reduce its lifetime faster. Okay. So why do this degradation process appears? And I was mentioning earlier the cell-to-cell variation. So one of the reasons for this is that you have manufacturing defects in the process of manufacturing the cells. So we need to also study the impact of manufacturing defects on the lifetime of the battery, on the battery pack itself, and ultimately, how does this impact the performance of an electric vehicle in which these batteries are actually used? So this plot here is showing the state of health with the cycle number again, and the bands here are showing the variation that happens due to a manufacturing defect. So this is done by, so we know from the manufacturer that there might be a small error on like the thickness of an element of the battery. So they can provide us that, okay, you have a 1% tolerance for this parameter, and we have like 0.1 tolerance for another one, or 2% tolerance, depending on the manufacturer characteristics. We can then plug this information in JuliaSim batteries, and we will estimate the remaining lifetime of the battery based on this information. And this here can also work with more complex charge-discharge protocols. I'm going to show a demo of this a bit later. Okay, so now let's go to battery pack analysis. So as I was saying, the aim for JuliaSim batteries is to bring accurate electrochemical models to the pack level so that you can also scale these very precise models to large battery packs. And here the technology that enables us to do this is a JuliaSim compiler. And here we have a comparison between the standard compiler, so the standard modeling toolkit, and the JuliaSim compiler. So JuliaSim batteries is implemented in modeling toolkit, and with JuliaSim compiler you can switch the compiler that is used to generate the actual Julia code that will run, or the actual code in the case of JuliaSim compiler. And this analysis showed that the problem is that I was saying in the beginning we have 300 DAEs for one cell. So when you have a pack which has 1,000 of those cells or more, then just the compile time of all of these equations will be prohibitive, and the runtime might not even be measurable in some cases. And with standard MTK, this is a challenge because we have just the symbolic structure of the symbolic representation of MTK is not able to handle such a large number of equations. So in the previous talk, it was mentioned that you have very complex equations, and you end up after simplification with a few of them. Here, it's the case where we have a very large number of equations, and with JuliaSim compiler, we are able to take advantage of the repeated structure. So one of the optimizations that enables this scaling is we are taking advantage of repeated components. So here, another thing that I want to present before the demo is a fast charging analysis. So here at the pack level, we want to look at how does fast charging impact the degradation and the health of the battery depending on how fast are we charging the battery. And here we have each band is one charging protocol. So we have 1C, 2C, 3C, and so on. And one interesting thing to observe here is that the distribution of the cells in a pack varies with how fast are we charging. So we can see that for slower charging, we have a quite wide distribution. So 1% of the cells reach end of life by cycle 826, and most of them so 50% of them, sorry, reach that by almost 900, so 899. If we look at the faster charging cycles, there we have a much sharper distribution. So with JuliaSim batteries, we can try to answer these questions. So because we actually model everything that happens, so we model at the electrochemical level what happens inside the battery, we can analyze this cell-to-cell variation and look at the cause behind this variation that we observe. And here we are looking at, in the first plot is the charging at 1C. It's cycle 899, so this is the cycle number where 50% of the batteries reach end of life. And we see that we have the CC region here where we have one charge for 2,800 seconds. And in this region, the red lines represent the cells that are below average, so that they're already under the 80% mark of battery health. And because they have been charged more, they have degraded faster, so this has impacted them more. And the ones with blue are the ones that haven't been charged so fast, and thus they have longer lifespan left. And we can see that if we compare 1C with 3C, the length of this interval here and here is significantly different. And this essentially is what would account for the difference in the distribution that we see for the cell-to-cell variation. So now I'm going to go to JuliaSim batteries. So this is an app that you find on Julia Hub. So it's right here. And it's available on Julia Hub. And for after you launch it, so this is the interface where you can look at the battery configuration. So you can choose the battery model, you can choose the chemistry preset. So this is the chemistries that I was saying that we support. We can add number of cells in series, in parallel, and we also have sub-modules for things like thermal dynamics. And after that, we have the experiment. So this is the charge protocol that we are using. And we can just run an analysis and see the results for this particular charge protocol that we have here. And just a sec. Also, in these options here, we have also defect simulation. So what does this mean is that for some of the parameters, we can include a distribution. So it's not just one single value in the parameters for the differential equations that we're solving. We have a distribution, and we run the simulation here. We have like 100 times over, but you can repeat it even more if you want. And
now you use some standard geometry
yeah.
design?
Yeah. So here, if you look at the advanced option, so this is shows even more detail on how does the configuration and all of the parameters. We can go in even more detail here and edit everything if as needed. Okay, just gonna quickly refresh it. I think that okay. So we're going to import. So you can easily import configurations, okay, and run. Okay. And if you want to cycle, you can also, so a more complex charge protocol is represented here. We repeat it a number of times. So this is, yeah, this is what I wanted to show. So we can look at several characteristics like power, state of charge, state of health. And we can see here at the first cycle, the state of health is 1. If you go more advanced, then it went under 1. So that would be the end of the demo, so that I can leave some time for questions. With questions or without questions? Oh, okay, thanks. I thought it was with questions. Okay, so as I was saying, here I have a more complicated charge and discharge protocol that is repeated several times, so that we can also look at what happens with varying the number of cycles and taking a look at what I was explaining earlier about the degradation and how does cycling the battery over and over impact the battery. Now, moving on. Okay, we can also do an analysis on if we have batteries that we received from manufacturer in several batches, we might want to see the impact of manufacturing defects. So we might have things that are off spec or have a very high defect variance. So the manufacturer might, depending on the characteristics of the batches, we can take a look at this and do more complex analysis in order to analyze the impact of the defects on the performance of the battery and the resulting things in which is integrated like an electric vehicle. This is then can be very useful in analyzing which defects are the most important ones in order to improve quality control, so that we know what defects we should target in the design process of the battery. And as I was mentioning, JuliaSim Batteries is built on top of modeling toolkit and is also integrated with the entire JuliaSim suite, so that you can do also all of the SciML. There's a lot of SciML talks here, so we have things like surrogate modeling. So you can take the model that you have for a particular battery, and if you want to accelerate that and just run that very fast and do optimization on that, or include that in processes that need to do quick estimations, you can use surrogate modeling. Or if you want to discover missing physics in the battery models, you can try to leverage the neural networks capabilities that are, so you can embed the neural network in the model, and this is work in progress into how to leverage the data that you have in order to discover missing physics in the model that fits the particular station that you have. So you might have a very custom battery model that you need, so your specific chemistry, you have data that you have acquired for the particular battery system that you are working on, and then that can be calibrated, and if that's not enough, we can go even deeper into scientific machine learning workflows and improve the models even more. So yeah, I think that's all. Thanks.
Thank the speaker. We have a person. Do we have questions from the audience?
So I guess I have two questions. The first would be if you could elaborate maybe a bit what happens inside the JuliaSim compiler, what makes that much faster. And
yeah. Okay, so I think there might, I'm not sure if there is a talk on this, but the main thing here is that battery packs have a very repeated structure. So you have cells that are in series or in parallel, and they are connected, and we have the same structure that's all over, that's repeated. And instead of generating code that has all of the equations one after the other, and you have a very large chunk of equations that it is gonna be very slow to compile because you'll have to go through hundreds of thousands of them, you can leverage the repeated structure and have a for loop, and that for loop then can be do SMI, can be vectorized. You can run that essentially in parallel, and vectorization at the instruction level. So it can be you can have very efficient code generation for that. And JuliaSim compiler also has a custom LLVM code generator, so we generate directly LLVM, and this can be, I mean, there are several things that help it reach the scaling, but those would be the important factors.
Okay, thank you. And the second question is, I worked with Modelica before, and I saw how people model battery packs with Modelica, and of certain interest was always like the interaction with the thermal system, because that affects the lifetime of batteries. So I wonder what the advantage of using the modeling toolkit compared to Modelica is, because I think here it's more difficult to integrate this system with thermal systems, for example.
So with FMUs, or what you're mentioning? What kind of systems? I didn't understand.
Thermal systems, so the cooling systems.
Oh, thermal system. Yeah, so here the model itself has a, you can enable thermal modeling inside the, so here there was a, so we have thermal dynamics. So you can, so the thermal dynamics part is part of JuliaSim batteries. So this is part of the model inside the JuliaSim battery. So it's kind of already embedded in there. And we are working on expanding that, but yeah. I'm not sure if that answers your question.
Yeah, and then the advantage of using JuliaSim batteries in comparison to Modelica.
So on that side, so with JuliaSim batteries being implemented in Julia, you have the full power of a programming language. It's not just a declarative language, and this can enable more advanced things. Like the way that you are building a model is you can leverage things like for loops. You can build things that you have programming language constructs that are much more powerful than a declarative language. Of course, there are trade-offs. So some things might be easier to do in a declarative language, and some things might be easier to do in an imperative language. So this is a trade-off right here. And modeling toolkit essentially shows itself as a declarative language, similar to Modelica, but it's implemented in Julia. So you have both of them at the same time.
Okay, thank you.
One more question?
Hi, thank you. You mentioned it sits within modeling toolkit. Can you combine like models of things like a vehicle inverter? You talked about the road test, and I understand how they work together.
So the idea of using modeling toolkit is that we want to have a common base in which all models talk, so that you can combine a different model that is from a different part of the entire vehicle or the system with connectors, so that you have standard connectors that you can use, like if you have mechanical or electrical or heat ports and so on. So everything speaks the same language at the fundamental level, and then you can use this to integrate systems. Basically, the idea would be to be able to take, like, I don't know, you have an HVAC system and the battery system. You want to look at how does running the HVAC in your car impact battery life and stuff like that. And using modeling toolkit as the groundwork for this is what would enable us to communicate between models from different teams, essentially, because each team has its own model, its own experts that build a very good model for a particular part, but then everyone has to integrate together, to talk together, and we're leveraging modeling toolkit for this.
Great, thank you.
So let's thank the speaker again with a round of applause.